Alright everybody, welcome back to Math 330. We're going to talk about applications for Chapter 1, Sections 1 and 5. So it's solutions of differential equations or separable differential equations and the standard form or using the integrating factor. And I'm going to show you how to use Maple to help you solve these differential equations. So at the end of this activity, a student should be able to do the following. Have Maple include the DE tools package, have Maple compute an integral, input a differential equation into Maple, have Maple solve this differential equation, solve the differential equation interactively using Maple, use Control-L commands to input equations into functions in Maple, use the right-hand side command to process information Maple, use the DE plots command to create slope fields and plot several solution curves, use the subs command to substitute information into the equation in Maple, and use a use a plot command to graph functions in Maple, and then find the limit of a function using Maple. Alright, so let's get started. What I'm going to do is talk about section 4 first. So chapter 1, section 4, and what we're going to do today is something called the logistic equation. So it's called the logistic equation, and it is an equation that allows us to model populations. So what is a logistic equation? Well, it's a derivative of some function. Why is that not working right? Let's get that up so we can see it. It's a function, it's a derivative of some function x that's equal to some constant a times x of t minus some constant b times x of t squared. Okay, what is a and what is b? A is usually associated with births in a population, and b is usually associated with death in a population. So that's why the minus sign is out here, is because this is going to remove things from the population. This is going to add things to the population. So this is called the logistic equation, and you're going to have to solve this for an applications manual. So we need to create some A's and B's here. So what do I want for A and B? I don't know. Let's see. Let A equal what should A equal here? Let A equal 0.2, and then also let B equal 0.05. Let's do that. Okay, so I'm going to use the Control-Alt command, and my font has changed again. So Control-L, and I want to get my differential equation back. So that'd be 1.1 according to these markers over here. And if I hit return, there's my differential equation. So we can solve this two ways. We can make it a separable differential equation and use integrals. So I'm going to show you how to do that first. So the first thing we have to do is separate it. Now if we separate it, we get two integrals, and we'll get one integral of dx, in which we have 1 divided by 0.2 times x minus 0.04 times x squared. And that's what we'll get is one side. And then the other side is just going to be an integral of dt. Let's put that in there, and then I'm just going to add my integration constant. right now okay, we'll add the integration constantly. So I'll hit return, and it is actually solved my integral for me. Whoops, wait a minute. That is not the right integral. Let's change that. It shouldn't be t, it should be just 1 because there's no function of t on that side. So let's do that again, and it has created my solution. Now I need my constant. So I'm going to do another Control L, 1.4, and then I'm going to add my c for my integration factor. I added it to both sides. That's not what I wanted to happen. Alright, so let's do there's a command called left-hand side and right-hand side. Right now I want the left-hand side of my solution. So I'm going to do LAHS, that's left-hand side, Control L 1.4, and then that's going to give me the left-hand side of my equation, and that has to be equal to the right-hand side, which is RHS, Control L 1.4, and then I'm going to add a C. There we go. That's much better. Alright, so now what we have to do is solve this differential equation, or solve for x. So we have to do some algebra. So it looks like I got factors. I'm going to divide both sides by 5. So let's do that. Control L 1.6. Divide 5. Oh, I did 6. Wrong one. Let's do 5. There we go. That looks better. Now, since we have ones up front, we can apply the logarithm properties. So I can rewrite this as log, natural log of x divided by x plus, or x minus 4. And that should be equal to 1/5 times t plus some constant. We'll just call it C1 for now. And now I can take the exponential of both sides. So exp parenthesis Control L 1.8. And I didn't like that. Okay, so what we're going to have to do is do right hand side and left hand side again. Left hand side, open parenthesis, close parenthesis, should be equal to exp of the right hand side, Control L 1.8, close, hit return. There we go. And now we can solve for x. I'm going to have Maple solve for x for me. So let's solve for x. There it is. Let's extract that out. So select item 1 twice. And now we've solved for x. What you're going to have to do now is figure out what the initial condition is. So population usually starts at some set population when at some set time. Usually we figure out that at about 0. So if we figure out initial condition, so what do we want for initial condition? Let's say initial population is 30. I have no idea if that is. We'll select 30. So I'm going to use the subs command, subs, square bracket, x equals 30, comma, t equals 0. Control L 1.12. And then that puts it in there, and now I can solve for my constant. So I'll right click on that, solve C1. C1 comes out to be this value. Let's extract that out to select ones, and then let's approximate that to 5 digits. And so C is that value. So if we wanted to plug that back in, so what I would do is go back to my solution that I had up here. So I want another subs command, and I want to substitute Control L 1.17 into Control L command, what is it, 1.12. And let's see if, okay, so there's our solution. We probably could simplify this a little. So let's simplify symbolically. Is that doing? Oh yeah, it made it all decimal places. Well, that's our solution for our particular initial condition. You're going to have to do a slope field. To do a slope field, we got to include DE plots, right, with DE tools, and then do DE plot of my differential equation. Where's my differential equation? It is right here, 3, 1. 1 point, okay, Control L, 1.31, and I do, sorry about that, and then I do that, and it's x of t that I want to do it, and I need to give it a t. It starts at 0, let's say it goes to 15, comma, and x, I have no idea, x probably going to start at 0 and go to, let's do 15 again, and let's put our initial condition in there, x at t equals 0 should be equal to, what did I have, 30. And I'm using a new way of putting in initial conditions. It's another one that's in there, so let's see what happens. There's our direction field plot. I don't see a solution curve. You definitely see down here that we have a straight line solution somewhere maybe around 4. Maybe it's starting way up here at 30. Maybe it just doesn't decay fast enough. Let's try putting it in the normal way. T is 0, comma 30. Nope, I wonder if let's change the x all the way up to 30 and see what happens. There it is. Just wasn't showing up in the range that we had put in there. So definitely comes down. So let's try an initial condition that is less than let's try something. Let's try 2. Start at t equals 0. The initial population is 2. So if we look at that, it definitely curves out to some limiting value. We can. Okay, so let's check to see if our integral we did is correct, and let's look at our differential equation again. So our differential equation, Control L, let's bring that back, and that was it. So let's solve this. Let's let DE solve this for x and see if our solution, and look, our solution looks pretty good compared to what we had earlier. We need our initial condition there. We can put that in there if we solve DE interactively. And if we do it interactively, I can edit my condition. So I can put an initial condition. X at 0 has to equal 30. Done. Oh, I didn't add it. X at, let's see. X at t at 0 has to equal x at 30, and let's add that. Done. So we want to solve it symbolically, so I'm going to click on that, tell it to solve. There's our solution. Let's plot it. Looks familiar. Looks like it's coming down here to 5. And then if you quit, it should return our solution that we found. That should match our solution right here. That's matched the solution that we had, except there's a little bit more math in there. We would have to do some algebra to see if they equal. I'm pretty sure they will. Alright, what's our next? Okay, so you're going to have to... Alright, so we've solved it with the direction field. We've solved it with having Maple solve the differential equation. we can also figure out what the limit is. So if I take our solution here, or the right-hand side of this, and take the limit as t goes to 0. So how do we do that? I want the limit as t goes to infinity. I have to put infinity, so I'm going to need Greek common symbols. There we go. And then I got to put my function in here, and that's the right-hand side of my solution, which is Control L 1.21. Hit return. It takes 4. So our limiting population is 4. We can only carry a maximum of 4 in our population. That is not a very robust population, I'd have to say. The next thing you're going to have to do is take your solution here, and at this particular initial condition, figure out how long it's going to take to, let's say, get down to 10, right? So to do that, I need to take my solution here. So I might need the population to be 10 at Control L. Let's see, I want to be the right-hand side. Control L 1.21. There we go. And now we need to solve for t. You do some algebra. Let's have the computer do the algebra for it. And so I need to extract that element and then approximate it to 5 digits. So in a time units of 1.8, I don't know, minutes or seconds, probably hours. Depends on all the units we're dealing with here, and I'm not sure what they are because they're population units. It's probably per day, so 1.8 days we're going to be down to a population of 10 if we start with a population of 30 with this logistic equation. Doesn't appear to be that great of a population model since it drops off that fast. But that all depends on the A's and B's you choose here, so that's up to you. So I can collapse this subsection down to that one. That was actually section 4. And let's create a new subsection and talk about applications for the integrating factor, how we can solve for that. Okay, so to do that, we're going to look at Newton's law of cooling again. So we're going to look at this differential equation. So let me type that one in. It's a Newton. Okay, so time t, the temperature of the object should be equal to a minus k times the temperature minus some outside temperature. But we're going to change this a little bit. The outside temperature can fluctuate around, it can change in time. Normally A would be constant. The outside temperature is relatively regulated, but we're going to make this a little more interesting by changing it. So you're going to need to be able to figure out how to plot, how to create this outside temperature. So you're going to need a high and a low. How do we get to the high and the low? I am going to you need to figure out some location you want to use. We can use Indianapolis. So to find this weather, you go to the National Weather Service site. It's weather.gov. And then you click on the state of Indiana. And if you click on the center, it will give you to the Indianapolis area. And then if you click on, then after that, you want to click on climate and past weather. And then you can choose a particular city in Indiana. You've only got a few to choose from. I'm going to do yesterday's temperature in Indianapolis, or today's temperature in Indianapolis. I want to look at the normal highs and lows that you have, and if that shows up in this graph, and that shows up under this heading of normal values. So the high and low temperature that we normally have is the high is 79 degrees for today, and the low is what? 57. And the average is 68. So if we get back to that, and let's go back to Maple. So you can pick any U.S. city you want to do. I believe the problem has you choose the summer of July, but that's how you get the temperatures you need to help you figure out solve this problem they're asking you to solve. So how do you get the function? So this is going to oscillate in a 24-hour period. It goes through a high and a low, and we need to be able to figure out how fast that's going to go. So we're going to need a trigonometric function, and the way we're going to do this trigonometric function is we're going to use a cosine curve of some omega. So where's my Greek variables? So some omega times time minus some offset, and I'm going to just call that phi now for lack of a better variable. But that's the function we need to do that, and we need to figure out what temperature it needs to be. So the idea is the temperature oscillates around a particular medium temperature. So our high was 79, and our low was 57. And if we divide those, alright, so we find the minimum, not the minimum, the average. So we have a high of 78 plus the low of 47 divided by 2 gives us 68, and that's 11 degrees. We subtract the average temperature in the day from the high. It gives you an 11 degree variation, and you want to plot out sines and cosines. So if we create this, let's get rid of this. So what do we have going here? So I got 68 minus 11 degrees times cosine. Now cosine will vary between minus 1 and 1. Well, we got to give it a period to vary over. The temperature is going to have to go through a period in cosine is 2 pi. It takes 24 hours to cover that time. So if I look at that graph, I get this graph. So high temperature is at noon, which is okay. Low temperature is about 22, 23 hours, somewhere around there. Seems like we're doing a good oscillation. The problem is high temperature is not at noon on the Earth. It's usually around 4 o'clock. So I have to shift this to the right 4 hours. And then I got to put that 4 hours in terms of the cosine, so it would be an angular measurement. So would it be a plus or minus sign to shift it 4 hours to the right? Let's try minus. So it takes 2 times pi takes 24 hours, and I want a 4-hour shift. So let's try this number, see if that works. That seems to work pretty good. We are about at 4 o'clock now, or 16. So this looks like a good formula for the temperature. Okay. Now it doesn't look like the one they have in the book, but what you have to remember is a trig identity. So let's do let's do that trig identity. We know that cosine of A, let's see, minus B is equal to cosine of A times cosine of B minus sine of A times sine of B. And it has done that for me for my A's and my B's that I've already defined earlier in this online lecture. So what are my A's and B's? If this is my function, let's make this my function, Control C. Let's bring it down here, Control V. That is my function of what we have to do. How do I get that? Boy, Maple has already shifted that to sine. Maple should allow me to expand that. Let's see if I can expand that. Simplify. by normalized expand. Let's try that. There we go. Perfect. So if you look at the function that the book gives you for this, now you can find your coefficients for the sine function, and now you can find your coefficients for the this should be the cosine of pi times 11. Cosine of 6 pi times 11. The 11 halves divided by 3 halves should be the sine of 1/6 over divided by pi. Alright, so that allows you to generate a function for a that oscillates in a 24-hour period. So if we do that and plug it into our new differential equation, what do we get? So I need to do that. So let's control L 2.1. We get that back. I need to make a subs. Command A of x equals what? Control L 2.6 comma Control L, my differential equation 2.8. Oh, I forgot to close off my equation. There we go. So there's our new differential equation. Well, if you look at that, that is no longer a separable differential equation, but it is one we can use the integrating factor for. You can multiply through by the k and bring out the t, and then you can solve that using the integrating factor, which makes it kind of challenging. So we can also solve it using DE interactively. Let's make the temperature at 0 equal to T0, and we'll add that, and we're done. We're going to solve symbolically. We're going to solve that. There's our solution. I don't think we can plot that because I don't have values of T0 yet. So let's just return the solution. So there's our solution to the differential equation. And you can select a T0 and a K and figure out, well, what can K be? Well, if you read the book, K says K can range between 0.2 and 0.5. 0.2 is a well-insulated house. Even if it's a really good insulated house, it can go down lower than that. And 0.5 would be a house with the windows open, or a very poorly insulated house. And then you can graph multiples of these functions. You could use the subcommand to change K. You could use the subcommands to change T0, so on and so forth, and make a graph, just like in the book, of different initial conditions to figure out what has to happen to the temperature inside the house before the air conditioning is fixed. All right, that's it. I'll see you in class.